We continue with section 8.1 today. Yesterday we looked at definitions and notation used for hypothesis testing. We focused on looking at examples and practice how to write out a null and alternative hypothesis. So today our focus is going to be on knowing the 5 steps of hypothesis testing and then looking at some examples of how to find the critical values for the z-test. All right, so again, we're focused on today the traditional method, solving hypothesis testing problems. The very first step is that we want to state the hypothesis and identify the claim. Step 2 is to find the critical values. 3 is to compute the test value. 4 is to make the decision to reject or do not reject the null hypothesis. And then we summarize the results. So when we start section 8.2, we'll actually go through situations that we conduct. We go through all 5 steps of the hypothesis test. Today, I just wanted to list them out for you, and then our focus will be on the critical values. All right, so again, getting back to a statistical test. This is a test that uses data obtained from a sample to make a decision about whether to reject or not reject the null hypothesis. The numerical value that we obtain is the test value. So the mean is computed from the data obtained from the sample and compared with the population mean. If the difference is significant enough, we reject the null hypothesis. If not, we do not reject the null hypothesis. So this is all going to help us with that step 4 of our hypothesis testing. So we're going to make a little chart for 4 possible outcomes. So just go ahead and draw this little box here. So we have 2 choices. We're either going to reject the null hypothesis or we do not reject the null hypothesis. And there's 2 facts about the null hypothesis. Either it's true or it's false. So just to write these out, if we reject the null hypothesis when it is false, that's the correct decision. If we do not reject the null hypothesis when it's true, that's the correct decision. What happens if we reject the null hypothesis when it is in fact true? We get an error. It's called a type 1 error. And what happens if we don't reject the null hypothesis when it's false? That's another error. We call that a type 2 error. Our main concern is going to be with a type 1 error. It's actually more serious than a type 2 error. Plus, there's type 2 error is not easily calculated. So just again, to write these out, a type 1 error occurs if we reject the null hypothesis when it's true. Type 2 error occurs if we do not reject the null hypothesis when it's false. So to kind of compare the seriousness of a type 1 versus a type 2 error, we're actually going to do this for a jury trial. So again, we're going to say that H naught is true, and then this would tell us that the person would be innocent. And if H naught is false, we're not going to say guilty, we're just going to say not innocent. Over here, we'll reject H naught. That means we're going to convict. Here we will not reject. That means we'll acquit. So if we convict someone who was found to be not innocent, that would be the correct decision. Or if we acquit someone who is innocent, that would be the correct decision. If we acquit someone who is not innocent, that's a type 2 error. That means we're letting somebody go, and chances are they're going to commit another crime and then maybe be on trial for that. So it is an error. It is a serious error, but when we compare to convicting someone who's innocent, that's definitely worse than letting someone go who is not innocent. But again, that could be debated. So just like at the end of yesterday's lesson, there's a few more things to know about hypothesis testing. We base our decision on probabilities. It's also based on evidence presented. If the evidence is strong enough, for example, in a jury trial, they would convict. If we don't have enough evidence, we would acquit. But nothing, remember this, we don't use the word prove, nothing is proven absolutely. The only way to prove anything statistically is to use the entire population, which isn't always possible. But again, we never prove the hypothesis true. We're either going to reject it or we do not reject it. And again, if the difference is large enough, the null hypothesis is probably not true. So again, the question is how large a difference is necessary to reject the null hypothesis? And this is all going to make so much more sense when we actually get into section A2 and we go through an actual test. But we want to pick a level of significance. This is the max probability of committing a type 1 error. And check out the symbol here. The probability of committing a type 1 error, we call that alpha. If we can connect that to the graph of this, or the curve, a sketching of a curve for the standard normal distribution, alpha is the area that's left over. And we saw that throughout chapter 7. The probability of committing a type 2 error is beta, but again, we're mainly working, we are just going to work with alpha. And again, our 3 common significant levels. Again, if we go with a 90%, a 95%, and a 99%, that just means alpha is 10%. Alpha is 0.05. So we're staying away from the 90, 95. We usually use that side of it when we're looking at confidence intervals. And then alpha would equal 0.01. So this would indicate we have a 10% chance of a type 1 error. Or rejecting a true null hypothesis. Now, in just about all of our examples, we'll be told what significance level to use. But if you were conducting a research study, a research report on your own, you would decide what level of significance you want to use. And you always decide that at the very beginning. You can't change it at the end if the results aren't coming out your way. You just pick your level of significance and then you just kind of go from there. right, so again, the researcher decides what level of significance to use. So this all comes together with finding critical values. And on a standard normal distribution, that is going to be our cutoff values, our z sub alpha over 2s, or our z-score. So critical value, which I abbreviate as CV, it separates the critical region or regions from the non-critical region or regions. So a critical region, if our value shows up in the critical region, then we reject. So that's a range of values of the test value that indicate the difference is significant enough, and we reject the null hypothesis. The non-critical region, or the non-rejection region, is a range of values for the test value where the difference was not significant enough, and quite possibly just due to chance. In that case, we do not reject the null hypothesis. So just as in our situations on that handout from yesterday, we looked at a two-tailed test, a right and a left-tailed test. We're now going to associate the sketch of the standard normal distribution with each one. But on each one, we're going to fill in the non-critical region and then the critical region. But pause the video if you still need to copy that down. All right, so remember we have two types of one-tailed tests. We have a right-tailed test and a left-tailed test. And again, we're just going to sketch the standard normal distribution for each one. So right-tailed test means we have some area shaded off to the right here. This would be the critical region. What's not shaded would be the non-critical region. And then just the opposite for left-tailed test. We would have the area shaded in over here. This would be the critical region. And over here would be the non-critical region. And with the two-tailed test, we just have shaded regions on either side. So we have a critical region here and over here. Non-critical region will be in the middle. So you can see the critical values we're going to find are just going to be the z sub alpha over 2s that we're going to be looking at. So we would need the z sub alpha over 2s for the two-tailed test, but just z sub alpha, or just our z-scores here for the right and left-tailed test. All right, so we're going to finish up the in-class examples on the handout that I gave you yesterday. So the directions here are to find critical values for each situation and draw the appropriate figures showing the critical region. So in example A, we're told this is a two-tailed test. And we're given alpha is equal to 0.10. So we're going to draw our figure here. And because it's a two-tailed test, we'll have a shaded region off to either side. So that means alpha altogether is going to be 10%, but in this case, alpha over 2 is going to be 0.05. So this would be the area alpha over 2 Same thing over here. This would be, we'd have two critical values, and remember they're still symmetric. So this means we have 90% in between. So this is where all of our practice throughout chapter 6 is going to come back into play. So we're going to go to our calculators. We're going to use menu 553. We're going to type in 0.05 for the area. And that tells us this critical value is going to be a negative 1.64. And then symmetric over here, this is going to become a 1.64. So our critical values are plus or minus 1.64. But they're tied into the z scores, or in this case, z sub alpha over 2. All right, let's take a look at example B. This is for a left tail test. Where alpha is 0.005. So that means we're shading this region over here. We would have a critical value right here. So this is really 0.5%. So that means everything over here would be 99.5%, because this is alpha all right here. And what's nice is because that's shaded to the left, we do the same thing. We go back to menu 553. The area we're typing in is 0.005. So our critical value here should equal, and it should be negative because we're to the left of the mean here. We should be getting a negative 2 point, looks like we're going to round up, negative 2.58. And then C is a right tail test with alpha at 0.04. So we're over here. This is alpha. And if that's 0.04, then the rest of this would be 96% because alpha is 4%. So we would have this critical value right here. So now when we go to type this in our calculator, remember we need to tell the calculator the area to the left. So we'll be typing in a 0.96. So we want menu 553 again, but type in a 0.96. We should be getting a critical value of 1.75. And it's positive because we're to the right of the mean. But that's how we calculate critical values. They're just called something different now. But it's the same process of using the menu features on the calculator. All right, so I'm going to give you guys worksheet 8.1 to start today. You'll have time to finish it tomorrow. I'm also posting the answers as a separate PDF. You'll see the solutions to the chapters 1 and 2 final exam review. So as you're looking over those, please let me know if you have any questions.